Hello, my name is Karol Gugala, and I'm from NMicro, and today I would like to tell you about an open source NVMe AI framework with an accelerator platform we did, and explain how it works, what we use there, and how we can use it, and then what it's good for. I would like to start with some background info that will just shed some light, to why we did things as we did them, and why we choose technologies that we're choosing there. So, as I said, I'm from NMicro. We are a technology company. We use a lot of open source, new methodologies, and we do services. We don't do products per se, like devices. We do services around software, hardware, FPGA, ASIC, and all that stuff. So we don't like reinventing the wheels. We do like reusing the technologies, reusing the building blocks that are already there, and creating bigger, better, and nicer devices, the nicer technologies with that. And we do apply the methodologies taken from the software to build that, even if it includes hardware. And one of the examples of those platforms, those devices we do, is the NVMe framework with the Accelerator platform that I'm going to present today. So just to be sure that everyone is on the same page, let's start with maybe some definition of what NVMe actually is. So NVMe is family of specifications around communication with non-volatile memories. So non-volatile memories, in most cases, those are the disks, hard drives of the computers that you basically use in your PCs or data centers or things like that. Less often on embedded devices, but sometimes also there. Each hard drive actually comes with is an embedded device running some firmware and some controller, but it's not often used with embedded devices. So the specification actually, the set of specifications, they do specify all the aspects from like hardware, electrical spec, through communication protocols, through like the organization and all that stuff. It does support various interconnectors and hardware protocols, hardware frameworks. The most popular is actually M2 connector with a PCIe bus for exchanging the information, exchanging the data between the device and the host machine. So if you'd like to know more, those are openly available. Just go to nvme.org and you can grab them. So as I said, NVMe actually specifies, how to implement and how to talk with the hard drives. So why do we talk about accelerators in hard drives? What's the point of that? Why do we want to actually have it? So as you probably know, machine learning is getting instruction from quite a few years, and it does process a lot of data. So typically, you run those algorithms, AI algorithms, on some dedicated clusters, computing clusters with some big GPUs or set of processors and so on. All of that requires moving a lot of data from some kind of a data center, from some kind of like a farm of hard drives, into the computing machine, process the data, write it back. So all the movement back and forth actually generates a lot of costs, and it's slow. I mean, slower than just processing stuff on processing data in place, and generates a lot of heat, consumes energy, generates CO2, and so on. So that's not really something that we want to do. So having an accelerator puts really close to the data, reduces that, mitigates the problem of data transferring. It also gives us another possibility of processing the data on the fly. So when it comes to the device, we can actually do something with the data before we actually store it. So it can solve a problem of storing sensitive data. For example, we have a movie, we have a video stream that films us, and we don't want to have like our faces. I mean, nowadays it's not a problem. We have all have masks, but back in the days, we may, people didn't want to have like their faces on like a video streams, and if you store like sensitive data, you have to, comply to certain regulations. But if you could like process the data on the fly and just store something that's anonymized, problem solved. You don't really have to comply because there is nothing to worry about. So having an accelerator there is actually pretty good idea, and it's actually pretty nice. And there is actually, ongoing ongoing work in the NVMe in the NVMe working groups on specifying a new set of commands, new set of new extension to NVMe that allows you to that will allow to implement those accelerators that can actually process the data at the place where the data is stored. So having that in mind, we and Micro, together with Western Digital, we came up with an idea of like building an open source platform where people can actually implement various accelerators and actually play with NVMe standard extensions to implement some new instructions, some new commands, new way of processing the data as it comes. So we decided one of the goals there was to build it extensible, build it configurable, build it in a way that people can actually play with it. Yeah, not only like a narrow group at Western Digital or at Micro, but wide spectrum of developers, researchers, and people around the world to enable them to just play with it. So that's why it's open source, to enable the people and to be able to configure the stuff, to be like very versatile. We decided to go with a platform that allow you to modify the logic inside. So we used Xilinx MP SoC. Xilinx MP SoC is a platform, is a SoC that comes with a few CPUs and FPGA. So in FPGA you can actually do a lot of additional logic. Western Digital built a dedicated platform for that, which is pretty nice. It actually fits into it is a form of 2.5-inch disk drive, so you can actually put it into your computer or into data centers or things like that. So that's really nice platform. But we also enabled the whole framework, the whole system to be run on like more standard development boards. This one is just one of the off-the-shelf development platforms for Xilinx MP SoC chips. It's not that nice and compact as the previous one. It's like that big, so it's not that easy to put it in your computer, but still usable if you want to just play with it. This is just buyable somewhere in online shops or whatsoever. So yeah, having the platform, we're able to split the system into two parts. So on the left side, it's displayed, displayed the same way I see it here. On the left side, there is a FPGA part, the part where we could implement all the logic we need, all the additional digital circuitry that we need to have to handle NVMe transactions. And on the right side, we have the whole SoC complex with Cortex-R5 and Cortex-A53 CPUs running some software that we want to use, we want to utilize. And the whole idea here is to have the FPGA part to handle the low-level connectivity for NVMe. Cortex-R5 CPU to run the software responsible for handling NVMe base command set, and the rest of the system for handling the rest. So what does it mean to handle NVMe command set. So basically, the specification tells about two types of commands. First of all, we have admin commands. Those are used for figuring out what kind of device we deal with. Yeah, so the host machine, if you connect a hard drive to your PC, the drivers on the PC side basically, ask the device, who are you, what can you do, what's your speed, what's your capacity, and so on and so on. So first of all, you have those sets of commands. Plus, of course, things like reset, like start, stop, power management thingies, and all those things. And the other types of commands is I/O commands. Those are used, of course, for moving the data. Like the drives are for moving the data back and forth. So we have this set of commands to just move the data to the device, from the device, and so on. So how does it really work? Let's get back to the original scheme. It works in a way that the host uses PCIe bus to access the NVMe control registers logic to write the data into it. So, for example, it wants if the host wants to send a specific command into NVMe, it just writes the register, specific register in this piece of logic. Yeah, this register can in our system can issue an interrupt telling the software on the Cortex-R5 on RPU to handle that, and the software, of course, does what it's supposed to do, like responds or handles the like transfer of some data and so on. When it comes to data transfers, we need to first get the command and like get some descriptor of the data transfer, like what data, how much data shall we move, from what address to what address, and so on and so on. So again, the software running on Cortex-R5 reads that, but then it talks to the PCIe DMA to either read from the host memory and get the data to the device, or write the data from the device directly to the host memory. And so that's the basics of how NVMe works. To handle that, to implement the whole logic of like NVMe transactions, we decided to go with Zephyr, and we use Zephyr on this Cortex-R5. Why we did that? Because, first of all, there was a Zephyr for that. There was a port of Zephyr for Cortex-R5. So it was originally added a few years back. Later, we added some updates to that and some functionalities allowing Zephyr to be controlled from the other CPU in the system. So that was like an obvious choice. We knew that it's there, it works, and and using Zephyr is pretty. Once you use Zephyr, it's pretty straightforward to add additional things. So Zephyr it was, yeah. So Zephyr it is right now, and that was the correct choice there. But since we have the configurable part, the FPGA part, we we got this problem of how to handle changes of the dynamic part and adapt the software, in this case Zephyr, to correspond to all the changes in the dynamic block. Actually, if you were here in this room yesterday on RISC-V mini summit, we had a similar discussion back then. Yesterday about how to handle like soft SoCs in FPGAs. But that's somehow related. We have maybe not the whole SoC, but part of the SoC that is reconfigurable and can actually change like memory mappings, can change whatever is there, and how to react for that. So normally it's pretty painful because you change one thing and you have to change the other thing. Like you change memory layout in the FPGA, you have to adapt the software in Zephyr, like at least header files with some definitions of where things are, but often a bit more of the code. Sometimes even like the whole handling of the way we handle some logic. And if you ever did a complex system, you know that it's impossible to maintain because you care about it, and at some point you forget about one single definition somewhere, or you misspell one single definition somewhere, and then it takes 2 weeks to figure out what's happened and then why stuff doesn't work. So, of course, there is an option to that, like generate all the changing parts on the fly. And we actually did talk about it yesterday, how to maybe address configurability from the perspective of this operating system. And one of the questions there was how to get the data described from what format to use to describe the platforms. So here we actually had the description because we were implementing NVMe logic and NVMe register set and all that stuff. So this is pretty well defined. I mean, there is a specification, an NVMe specification. The problem is that the specification is in a PDF file or set of PDF files somewhere on the internet, and it's not really machine readable. But fortunately, there are some like Python libraries. Python has a solution for everything. So we extended the whole build process with a few Python scripts that reads the PDF and generates the whole logic, underlying logic, like RTL code. In our case, that was Chisel. And then Chisel generates Verilog. And of course, the C code and header files for Zephyr to do that. And since Zephyr application, Zephyr build process, like for applications, that one relies on CMake, that was pretty easy to inject this dependency, like just first generate and then use it during the work. So with all of that in place, we had like a base NVMe device. Yeah, so we were able to connect the device to a PCIe. The host did some like initialization, talked to our code in Zephyr, like our application in Zephyr, and we were able to to have a hard drive. But that's not really something that we want to have, like just to have NVMe, because just to have an NVMe device, because that's you can buy it. There is a lot of already ready-to-use device. There's nothing really fancy with implementing the same thing again. We wanted to have a platform that will allow you to extend the whole system with additional functionalities, with additional commands, with basically NVMe protocol extensions. So we thought like extending embedded software running on some microcontroller. Every time you want to add something, it's not that easy. It's maybe it's not very hard, but it takes a while to reboot the device, to flash it, to check what happened, and debugging is not that easy. Of course, we have Reno, so we can debug things to some extension quite easily, but still, experimenting and iterating with embedded software is not that easy. So we thought, like, what if we can delegate all the unknown commands to Linux? We have the second CPU. We have the Cortex-A 53, which is quite powerful CPU. It's a quad-core, 64-bit ARM. Unfortunately, ARM is not RISC-V, but we're getting there. What if we can delegate everything? And we implement exactly that logic in Zephyr. So Zephyr basically handles all that it knows. And then if there is something that we don't know about, we can simply send it further. So how to do that? So fortunately, Zephyr comes with pretty nice openAMP integration, so we could simply use it. Linux also has openAMP integration, so we just enabled openAMP on one side, openAMP on the other side. There is a support for this exact platform in Zephyr and in Linux, so that was pretty straightforward. Yeah, we just enabled some functionality, and then we were able to exchange the data between those two asynchronous systems running on a single chip, on two different CPUs there. So yeah, we finally were able to do that. One of the comments we introduced, one of the extensions we introduced on a very first stage of the development was a functionality of running your own code on the device. So basically issuing a special additional instruction that is not one of the standard NVMe instructions that allows you to say to send a payload with some like firmware or like program to be executed on the machine, and to not to avoid being architecture specific. There we choose to use BFM. BFM is Berkeley packet filter, BPF, sorry, Berkeley packet filter, which is widely used in data centers. So all the people that work with data centers and like with handling storages and all those things, they actually familiar with that. So they know how to write this code. So BPF is originally injected into kernel, but there is a user space implementation. You can run a virtual machine in user space in Linux and just execute this code. And then you can either use it in a compile it to bytecode and execute it as a bytecode, but you can also execute it as interpreter, like run virtual machine in interpreter mode and just interpret the program and run it as like Python or something. So yeah, we extended the whole stuff with functionality of uploading those like binaries, I would say, and execute them on a device and write them in a way that you can, for example, say to it like take 5th block of your hard drive and do something, and then write it as 20th block or something like that. So in the end, you can simply read back 20th block and have the data. And since we were targeting AI acceleration, we didn't want to re-implement the whole AI stack, machine learning stack in BPF, because that would be maybe not the best idea to do. So we integrated something that was already there. And since we previously worked with TensorFlow Lite and we did like a port to Zephyr, we knew how to use it. So we extended the virtual machine to support bindings to TensorFlow Lite. So your application, like BPF application that can be sent to the device, can right now utilize TensorFlow Lite and can utilize models from built using TensorFlow Lite. So we're almost there. We can, right now upload software. The software has a model. Upload the model, and the software can use the model to process the data. The only missing part is it will be terribly slow, because those are like just ARM cores that would be slower than processing the stuff on your PC or somewhere else. So we need an accelerator. Fortunately, there are accelerators, and there is a VTA, open source accelerator that you can simply grab and adapt to your needs. So we did extend the system with VTA and just extend TensorFlow Lite with delegates that standard TensorFlow processing can use to delegate some computations to the accelerator. So in the end, you can have like all the flow, like connect the device, have the NVMe have detected it as NVMe, fill it with data, upload the model, upload some processing software, and process the data on a device. And with all that in place, we're actually able to, yep.
So I see IP core. Does that mean these accelerators are on the FPGA?
Yeah. So yeah, this is, I should probably say that that's a very good question. It is in FPGA. So the FPGA in this platform is pretty big, so we still had like a spare place to connect the accelerator and use it for processing this. Of course, this is just a development platform, so in the end, once you play with it and once you figure out what can be done and should be done, you can harden the design and proceed with your dedicated accelerator for your data center and stuff like that. Okay, so what next? Okay, yeah, I'm actually almost at the end. Yeah. What's next? The next step is to release the code. It actually goes through some cleanup and like some checking of like cross dependencies, all that stuff. So I suppose it's gonna happen next week, but I don't want to promise you that. So I put 2 weeks here. It should be released on Chips Alliance GitHub. If you don't know Chips Alliance is also Linux Foundation project, Linux Foundation organization. So I mean, organization that is under auspices of Linux Foundation. We should the code should be released there within the next few weeks. Just to sum it up, so with Zephyr and all those open source building block, we were actually able to create like a platform, a framework for all the researchers and developers to start working on, to enable people to work on like extending existing specification, existing NVMe specification, implementing new accelerators, implementing new ways of data processing, and hopefully in the end, build a platform that will allow many people to work on that, because having the accelerator near to the data is pretty nice idea and can actually solve a few problems that we have in data centers and when we want to process a lot of data. Okay, so thank you for your attention, and I'm happy to answer the questions if you have any. There's one there, yeah.
Hi, that sounds really amazing. I was a little bit late and I regret it deeply now, but just wondering, in terms of openAMP, I'm not too familiar with it. Is it something that is kind of like variable length messaging as well and structured messaging?
Yeah, that's one thing. And the other thing is that with openAMP, you can do this like synchronization, messaging synchronization, like mailboxes between two systems that are actually running independently. So you can have like a shared memory where one system actually writes data and just pings the other one that the data is there. And of course, it maintains all the atomicity and cache coherence between the systems and all that stuff. Yeah. So yeah, that's basically that.
I hope it's okay. Can I ask another question?
Sure.
So with NVMe, I think it's like a 48-byte built-in command size, right? So did you find it to be any kind of limitation that you occasionally had to use longer messages with openAMP? Or was it like not a performance factor at all?
So no, we didn't have like we didn't focus on the performance of the first place for resending the because openAMP is actually used for handling all the additional or the non-standard instructions. Like so, non-standard in a way that we don't know about them in Zephyr, so we just send them to the application in Linux using this remote proc openAMP way. The rest of the system, like the one that should be efficient, that should be fast, like data transferring back and forth, is done with standard instructions, and those are handled directly by Zephyr, by this Cortex-R 5 and the DMA. So in the end, you have this queue with transactions you have to do, and then we just tell DMA to just grab this data from that much data from this address and put it there in like block something. And in the end, the additional, the custom instructions, they are used for more like controlling the flow of the accelerator. Because if you want to upload the firmware, like the program for accelerator, you just write a BPF somewhere with a regular NVMe command. If you want to feed it with data, you just write data somewhere to the disk. If you need like a model, you just write a model with a standard NVMe command, and then you say load a program from like block 13th, use the model from block 20th, and process the data starting at 10th byte and 10th megabyte, and use like the next 2 gigabytes of the buffer to process it. Yeah.
Can I ask one more question? Sorry. So, am I correct in assuming then that you've implemented an eBPF backend in Zephyr?
Mm-hmm. No.
Oh.
eBPF is running purely in Linux.
Okay.
Zephyr just transfer the data and pings the application in Linux to process the data. So to run eBPF. So we don't run eBPF in Zephyr.
Okay.
But that may be actually interesting idea to run some. Yeah.
I was just gonna say like maybe a JIT might be a wise idea at some point.
Yeah. Actually, looking at since it's pretty easy to run like POSIX applications in Zephyr.
Yeah.
eBPF. Like maybe doing JIT in eBPF may be a bit more tricky, but maybe it should it could work, because you just have to write the memory with generate instructions like machine just machine instructions and just execute them. So that's not that hard, to be honest. Yeah. So
Okay.
yeah.
Cool. Thanks. I didn't mean to monopolize.
Okay. I think. Yeah.
No, I don't have any questions on Discord. Okay. Oh.
So were you the first project to target eBPF for TensorFlow Lite? Like, did that exist, or are you the first people to do that?
I haven't. I mean, when we were doing that, we haven't found any implementation of that. So maybe we were first. Hard to tell. It's like.
Yeah, I mean, it's a very. Yeah. It's an idea that never occurred to me, and But yeah, I get it. They do. People do it in the data center. They do that kind of stuff. Why not do it on the edge?
So yeah, that could be like the very first time somebody did it. It wasn't there actually. We were first of all, what we do when we start implementing new stuff, we check if it's already there. If it's there on and it's open source and a correct license, we reuse whatever we can. But it wasn't there, unfortunately.
Cool. Thanks.
Any more? Okay. Thank you, Karol.
Okay, thank you.